So RRG enables next generation AI. One of the things I've been talking about a lot on the internet is the fact that AI today isn't meeting the needs of people that are trying to make it work. And language seems to be the cognitive science that's been missing from today's AI. So what I want to do today is take my recent book, How to Solve AI with Our Brain, The Final Frontier in Science. From my perspective, the brain is the missing element in artificial intelligence today. We've got a computational model which does great things. It's really good with these iPhones and things, but it's not a really good model for how our brain works. I'm going to talk about that today. I've broken this into 4 parts. So statistical AI, which is the paradigm today. The fact that with language learning, what our brain does when we learn a language is radically different from what an AI device would do. So if we want to emulate something on an AI, that's got to be a different function to what we do with brain science. And we've got a new company we've just started. We're the commercial guys here today, and we'll talk about what it is we're leveraging from science in order to improve language learning. I'll also talk about progressing AI, because there's something that's been missing for the last 70 years in AI that our brain does and that machines don't do. And finally, tie it all together with RRG. And I'll probably talk a lot about RRG because that's been the basic science since 2012 for me, when I discovered a book by Emma Pavey that pulls it all together. So why is statistical AI in crisis? Well, what's the goal of AI? It's to emulate humans. So here's a list of 7 things that I put in the book that are just obvious. Automatic speech to text. Well, you can talk to your iPhone or your device and it will convert what you're saying into text, but it's usually wrong, or it's often wrong, and so you can't rely on it. We hear a lot about driverless cars. Imagine you can get anywhere in the world by just hopping in a driverless taxi that turns up, it takes you somewhere, you get out, and it goes on and does more work. It doesn't work at human levels today, and there's danger associated with it. And maybe, digital agents, these are the things which have been promised to replace 300 million jobs in the next year or something. Right? It's not happening because it doesn't work, because it doesn't have RRG in it. My thesis today is that the missing part of AI is what animal brains do. So it's motion, it's sensory input, it's the ability to understand context, and that's obviously a link into RRG in a moment. Oh, here we go. Here's the diagram that I love, because in RRG we have this linking algorithm going from syntax to semantics, and we've got this thing called discourse-pragmatics that for the last 8 years I never really understood what it was. I was always talking to Van Valen about context, and he always kept nodding, and I'm thinking, well, why is he nodding? It's called discourse-pragmatics, and then it turns out it's kind of the same thing. So thanks, Van. Next. So this model looks very much like a really good model from 125 years ago. So here's the semiotics model of signs linking to some sort of meaning. And the reason AI is too simple, there's the Albert Einstein quote, make science as simple as possible, but not simpler. Well, the 1956 model of formal linguistics factors out meaning. So you can do your parts of speech analysis, and you can produce very complex parse trees, but it wasn't including meaning intentionally. The other model that we're using now is this vector transformer model, and that one's based on, they keep blaming J.R. Firth for it, because he's got this quote, "You shall know a word by the company it keeps." And that's in his section of the book where he's describing collocation of words. So, if you're talking about collocation of words and you're factoring out then his context of situation, you get into a problem. But today, all of the work that we're seeing going on in Silicon Valley, pushing out these large language models, is all factoring out meaning and pragmatics. So what we're doing is bringing this green bit back in, which is predicates and reference. I use this term because the part of speech model is giving us a good overview of the syntax, so nouns, verbs, adjective, adverbs, prepositions. That's great from a syntactic point of view. But what we really want is to look at the meaning. So I want to take the words in a language, words and phrases in a language, convert it to meaning, and then only manipulate the meaning in order for us to carry conversations out with machines. Why is this important in computer science? Well, this is state of the art for what computer scientists are doing, and when I look at this, all I see is syntax and words, and I don't see any semantics, and this is the semantic diagram. So here's Arnold Schwarzenegger. So there's a referent written in English, and it's connecting via this English phrase, governor of California, which is a US state, but he's not actually he wasn't the governor of the state. He was actually working for the organization in California that managed it, and he was the governor of that. So just saying California is not enough, putting this in English isn't enough, and saying Arnold Schwarzenegger is not enough because he's done lots of things other than Predator, which is a movie, but you need to drill down to that as well. When, 1987, that's when it was released, who was in it, and so forth. And then here's a nice taxonomy model of dogs is animals, is living things. Well, I'm not sure what happens when the dog's not alive anymore, but that's the graph that is being used to... a lot of people are saying that these knowledge graphs are going to be the next big thing to fix large language models. My argument is that can't fix it because it's not accurate enough. And where could you get a semantic representation of language that includes things the way languages work? It's RRG. This is just the more this comes from relationship model. That probably sounds better. This is how they're referring to entities, nouns, and then you've got these verbs here, which are attributes and things, and that there's lots of predicates that get put in as attributes, which should probably be retained with the RRG layered structure of the clause. And I've just stuck down here derived nominal, so I put it on the predicate end. And now with lots of colors, this is way too much to see in such a short talk, but so the reference are these entities, predicates are these things, including our nominal RPs. And we're thinking of things as nouns in the entity space in computer science, and we think of relationships as verbs. And the problem is with nominals, they're still predicates, but they're used as nouns, and so you can't draw a semantic diagram accurately if you're going to confuse what the meaning of something is. So here's one of the ones that I use just to introduce what the challenge of language is. So you can just enter. So we've got this nominal phrase, John's purchase of the Porsche at the stadium yesterday, and the question is, what does it mean? Is it the blue line? Is it that whole thing that represents that clause? Or is it the old man saw the purchase at the stadium, go back up, at the stadium yesterday? So is the seeing at the stadium or is the purchase at the stadium? And the answer is in written form, we don't know. But but the point I would make is that what people say is according to Grice's maxims, and all of my really good ideas come from Van, so I'm just kind of repeating what he would say. But Grice was a guy at Berkeley, and he was talking about how do you interpret these things, what do people do? And people don't make an ambiguous statement. If you wanted to say the old man unambiguously, you'd probably front it with at the stadium yesterday, the old man saw John's purchase of the Porsche, and then you're done. And so we can probably trust people to say the right things. Just quickly, today's large language models are causing problems because they burn energy at an unbelievable rate. There's proposals for $7 trillion to be spent on data centers because that technology requires lots of GPUs. It needs lots of cooling and so forth. It's got serious problems, and it doesn't produce great answers because it's using statistics across phrase boundaries. In RRG, we have this concept of RP, which we can resolve before we resolve the layered structure of the clause. And as a result, we can actually determine the constituents first and then find patterns. So using the RRG model, we can run these things on a laptop. You don't need a new data center for it. You don't need GPUs. This is an example of just the work that goes into a large language model recognizing a sentence. Each one of these things here, a fluffy blue creature roamed the verdant forest. Each one of those is represented in OpenAI by 1,200 numbers. And then they multiply those 1,200 numbers by each of the ones next to it without knowing what any of it means. And then they choose, based on statistics, that a fluffy blue creature is some sort of phrase, so they'll add up their word vectors there. We've got our predicate roamed, and the verdant forest again has that. So every time you try and do something, it's just a massively computationally intensive model because it's all statistics. And in RRG, the system that we've used is there's our predicate, active accomplishment, the word eat, and then we're taking the first RP, we're taking the meaning of the first RP, which is just the referent and hamburger, and then we can check, because we know what 8 selectional restrictions are, so we can say, well, is man complying with the selectional restrictions? Well, if man's an animal and animals can eat, that's probably good enough, and if hamburger is a type of food, then that's something that you would eat. And so by simply building up this network, we're able to disambiguate and throw away most of the possible syntactic possibilities just by resolving it with the predicates. I'd like to show this one to the public because when you're talking about AI these days, everybody knows that it's just amazing. It's progressing at this unbelievable rate. And so here we go. This is 1956 AI Dartmouth. It's showing the people that attended: John McCarthy from Dartmouth, Marvin Minsky from MIT, an IBM guy, and a guy from Bell Labs. And look at this. Notable attendees included Alan Turing. That's just remarkable. So this is 1956. That's generated by a large language model. And now let's compare what Wikipedia says about it. So there's Alan Turing at the top from Wikipedia. June 1954 was when he died. This took place in the summer of 1956. So I'm pretty sure that Alan Turing wasn't a notable attendee at all. And that's the problem. If we've got a system like this that can't generate accuracy, what good is it? And here's another one. There's a few people in the semantics field at the moment that are very interested in improving AI, and they're looking at things like knowledge graphs. But it's if I put in the Wizard of Oz is a good man, now who do I mean? So as a person, you'd say, do you mean the book? Do you mean the movie? Do you mean somebody else? In this case, I'm referring to the Wizard of Oz being my neighbour's son that calls himself the Wizard of Oz, and I want to talk about it. But what the large language model does is it just gives us this great dump, and it illustrates the difference between, I don't know if these are the right terms, background knowledge and discourse, or immediate common ground and general common ground. So there's no immediate common ground in this system. There's just the statistics that are being manipulated by the general common ground. So we've got background knowledge with statistics, and it's not good enough for human language. But don't believe me. I'm just a guy that's been working on this full time since 2006. This guy here, Tom Dietrich, is one of the machine learning gurus, so fellow of the AAAI, and he's a fellow of everything. And he spent 2023 going around the US talking at universities about the limitations of large language models. And he pointed out that they're models of knowledge bases, not knowledge bases. They're statistical models. And so the reason it can give errors is because it's a statistical error. They're expensive, but what he wants to do, and this is why RRG is so critical, he wants to separate linguistic skill from world knowledge, right? Because at the moment, the reason they go through every document in the world that they can get their hands on is because that's where their syntactic patterns are coming from. Record and retrieve from episodic memory, which I'd say is immediate common ground, and create world knowledge that's general common ground. But there's many details to be worked out. I don't see them here today, and that's why the details have to be worked out, because we're not integrating RRG with the AI people and the computer science people. Okay, so that's my background in AI. Let's just move on to this new project, which we're launching today. Revolutionary language learning, and we're using science in order to improve on it. Speech Genie is the product with the cute little guy there with his little turban, and Language Parents, the company. The goal is to teach anybody to learn human language in 6 months. Do machines learn? Well, machine learning was coined in the late 1950s, but the concept of learning is really a human concept, and humans learn language. Machines get, I don't know, programmed to handle language, or they get statistical models that help them. So what's different with human language learning? Chris Lonsdale, who's one of our co-founders in the new company, he was living in Hong Kong, and he had a lot of English expats that were there. So some people from England, some people from the US, and he was going to teach them Mandarin. So native language is Cantonese in Hong Kong. And as he started teaching these people how to speak Mandarin, they came out with very strong Cantonese accents. So why would that be? It doesn't seem possible. They only speak English. They might have been in Hong Kong for years, but they're speaking Mandarin with a Cantonese accent, and he had to work out how to untrain that. So he came up with this model of brain soaking, which proved to be very effective, where just put on some headphones and listen to somebody speaking the native language, and they start to pick up how that language is put together. You don't normally see this when you go to an adult learning school, but Chris found that for adults that weren't speaking the language, this was a really effective technique.
Did you want to finish?
So the question is, if you're just listening to the language, what's going on in your brain? And so here's our temporal lobe. This area here is auditory cortex. When you're listening to things, your ears automatically are connected to your auditory cortex, which then has levels of resolution. What is probably happening is this area here, when it's listening to somebody speaking in, say, Mandarin, it's storing those sound patterns, and through babbling when we're very young, the Broca's area, around the Broca's area, you're able to then convert the sound that you've heard into muscle control in order to speak. So I did a bit of research just for today, and Patricia Kuhl from University of Washington, I watched her 2010 TED Talk, and she was pointing out these things like infants use their computational abilities to crack the speech code, which I didn't find helpful, because I was young once and I didn't have any computational abilities. Children absorb the statistics of the language, they're taking statistics, and after when they get to 12 months old, they've lost the ability to recognize a lot of the phonemes from other languages that when they're slightly younger they've still got. But the alternative is we can remove the processing metaphor. So click Beth. So how would you learn the statistics of language? I mean, that sounds like a really good computational problem, and maybe a computer could do it. But for a human brain to do it, the argument is it's the same match. So in a computer, if you see the word cat, you store it in a memory location. If you see the word cat again, you store it in another memory location. And if you see the word cat again, you'll store it in another place. And so you can have that word cat spread right across the internet, always referring to the same thing, but having no way of getting to what that answer is. In a brain, what pattern theory says is that we only store things once. And so if you've got the word cat, you store it in that auditory place that you've recognized it, and then if you continue, like caterpillar, you start with cat and then you add or pillar, or cat of nine tails, it starts with cat, or just plain cat. And so this way it gives the appearance of recognizing phonemes, but in reality all you're doing is learning the things that are the same, and then connecting them as you hear more. This was the age of acquisition of new language. This is apparently undisputed. We've got 7-year-olds that learn language really well, and then as we get older to 17, people get worse at it. So this is bad language ability, and this is high language ability. And over there, that's the concept of the phonemes not being recognized after 10 to 12 months, because the children's brains are simply focused on the phonemes that they're learning. So So my goal with this new company is to prove this wrong. What happens at 7 years of age? Well, people start getting taught differently. So when you're a kid, your mother and father can be talking to you. They can emphasize the sounds that are important. And after that age, you're potentially going to school. And one of the reasons people don't learn language very well is how do you teach somebody here's the sounds of a language? It's not the sort of thing you teach. You have to learn it. And you have to learn it through experience. So what did Speech Genie teach us? Well, part of the research is that languages are small. In Silicon Valley, languages are huge. You need hundreds of millions. You need every word that you can find. But you can, as a native speaker, you can create a sentence nobody's ever heard before. You can create words nobody's ever used before. So the statistics show that 3,000 words is pretty much covering all of language, depending on who you are. So I've got, this is a visual book. It shows Japanese by pictures. It's got 6,000 words that it shows in there. This is the basic German vocabulary that has a lot of useful statistics. It has the top 4,000 words to be fluent in German. And what I think that means is that the hard part of language is this basic stuff. The easy part of language is then adding in street names and other things. So Beth? So above here there's 3,000 words, and of those 3,000 words, a lot of them are those common nouns of categories: dog, cat, animal, table, furniture. Down here we got those very special words that we seem to use extensively, the immediate common ground, proforms, pronouns, contextual words. I don't know what hello means, and I've been speaking English for a long time. I don't know what yes or no means just by themselves until I'm actually in a conversation. So they only belong in that immediate common ground area. And so it's all about context. And then down here we've got the specific cases. So if you're talking about calcium and lithium as atoms, great. There's an infinite number of those things we can keep making up. So before we get into the RRG, how are we going for time?
Got another 20 minutes.
Okay. Let's just look at this thesis of what is our brain doing. Okay, so I'm just
Press
one
it,
more click.
Click it again.
This has just happened in China. These are the best robots from all of the universities that are competing. I think there were 7 universities. And I don't know about you, but this doesn't look human-like to me. There's something missing. That poor guy is going to get up. Yay, we've got a goal. Okay, so something's funny about the way they walk, the way they're put together. They're only very little. You'll notice that rather than have a big pile-up, this guy's come to save them. Okay, so that's the best robots in the world, and if you follow the internet, the progress is breathtaking. They're going to replace us all, I don't know, in the next 12 months or 2 years with this. Those are the things that'll be driving your driverless car at the next RRG conference. Okay, so here's the alternative. What's this fella going to be able to do? So it's a dog. I'm bouncing a ball here. It's changing direction. The surface is uneven. We're on the side of a hill. And it's going to jump up and catch a ball. Sorry, bad camera work there. All legs are off the ground. There's a victory lap coming up. It can do the same thing even if it's wearing a jacket. And this is a 180-degree turn, so it's turning completely around in order to catch this ball. And for me, that's poetry in motion. This dog never falls over. I can play this game all day, it will never fall over, even if the conditions aren't as good as that. And now if we compare it to the best robots, the best robotics that are around today. So this is just another view of it. Here's an industrial robot, $190 million project spent on this to date. And its job is to move around boxes. That's the vision it has, not quite human-like. That's not very good vision, which means it's limited with what it can do. And the Tesla robot, it's got touch sensors, so it can feel the egg, it doesn't break the egg, but look how it drops it. Right. You don't position the egg above the egg cup and then drop it. You place it, you feel it going into position, and then you take your hand away. And I don't recommend anyone do this at home. This is how robots stand up. Oh, that was a sharp cut.
Oops.
What's missing from AI today is complex events. So if I talk about RRG 2025, I know a number of people in this room now. I know where it took place. I can say a lot about it. But the question is, how would you represent this in a computer? And a computer person, because I'm one of them, would say, well, what you do is you design a database and you have people, and then you define what people require, and then you define what rooms are, and then you define shapes of rooms, and then tables, and it's an impossible task. There's something fundamentally different about what computers do to store this sort of information and what people do effortlessly. And as we saw, the dog running after the ball, my argument is it understands context. It knows that ball isn't just a particular shape. It knows that it's made of rubber, it can catch it in its teeth without hurting itself. It knows that as it moves through the air, it'll have shadows on it, and then it won't, and it copes with all of that. So context is stored by dogs, and my argument is it's basic animal function. I think fish probably have that level of capability in their brains. Okay, so how do we exploit RRG on machines? So my argument is that for each country, they should be managing their own language sources. So it should just look like a dictionary. It should have the link between the word, form, and the meaning. And the system should then cope with it after that. Whether it's writing or speech, it should all be controlled in a central group because we all speak slightly differently depending on our locality. And if we focus on this, then you can use it in industries for particular applications like banking. And hey, we can even teach people how all of this stuff works. The concept of knowledge doesn't need to be a part of the early systems. We can go and build useful tools that we communicate with without having the knowledge of physics and chemistry and biology and legal and multi-country everything. So how does my system work? Well, in order to do conversation, because I'll just take you through the specifics of it, I've used these old RRG terms just so I can quickly identify what's the same and what's different. Van is not happy that I'm showing something he did in the 1980s, but we're just taking some labels that we can use for a state or activity, one role, two roles, and there we go. I've got examples there, but we'll just keep going. One more click. So what this is showing now is how the system works in practice. We read in some text. Here's our immediate common ground list, which we're going to keep sequentially. We beat the Facebook conversational tasks by getting 100% on it using this technique in 2017. And then when some text goes in, we generate a response. If we're putting in a fact like Mary picked up the ball, then we're just going to say sure, yes, or some random acknowledgement. But if we ask a question like this one, what we do is we go to our immediate common ground and see, is this something that we can answer? And if it is, we then shortlist it. Next time we see a question, yes, Beth, can you, I think, hit space? Nope. All right, well, oops. So what it does is, I'm technical support here too. Sorry. Okay. All right, so I'm just waiting for a question. Where is Sandra? Yes. Okay. I give up. I'll show you the real thing. So what it's doing is by simply understanding what the question means, it can then look at what's in immediate common ground. If it finds anything that's consistent, which I call intersection, we then pull those out, and then the answer comes directly from the context. And this is what's under the covers of the system. These are meanings, and inside the meaning we'll have some definition. So for English, this won't be the final form, but for English we've got meal and meals being singular plural nouns. And for a verb we've got eat, eats, eating, ate and eaten, so just the 5 different forms of English. And we put attributes there because what we want to be able to do is have destruction have the same meaning as destroy. So we want the meaning to be whatever destroy is, and we want the word to tell us that it's destroy plus whatever we need in order to handle the syntax. And over there we've got selectional restrictions, which are done at the meaning level as well. So this looks like it's really expensive, right? Because we have to go through the entire language methodically and find out how do we build all of these phrases. The presentations today show the skill involved in identifying, relative clauses versus, is this an actor or undergoer, and is it some other type of subordination. But the point is that if we do this once, then you can use it for as long as that language is in business. So, maybe 10 years, maybe 50 years, maybe we tweak it a little bit along the way. And the comparison is large language models, 100 million to build, and they might have to rebuild it 3 times in the year. So there's a lot of expense going into the statistical model. I think we can do these things once and use them for years. Okay, how are we for time? Do we have any time?
You've got 10 more minutes.
10 more minutes.
Or 11.
So let me spend a couple of minutes just demonstrating this. And I'm going to do it on this side so that my head doesn't explode. Okay. So, oops. Just have to get my cursor over there. Okay, so thanks. So you can see here, this is just the interface, and if I go to categories, we've got a whole bunch of samples set up for different types of things. Pronoun resolution, for example. I won't run all of these fully, but this is one of the examples from the 2005 book, Beth arrived, she saw Sam, he kissed her. So we've just put all of that in at once. It's recognized the meaning of the first sentence, then the second, then the third, and the pronoun resolution takes place based on what's appeared already. If we look at the current context, we've got Beth arrived, she saw Sam, he kissed her. And if I look at the details here, she saw Sam, we've resolved the fact that Beth saw Sam, so we can store unambiguously the information that was put in. And if we then go back to the conversation and we ask one of these questions like who kissed Beth, it should say I don't know.
Sam did.
Oh, he kissed her, so that's okay. Was Beth kissed by him? So active,
yes,
passive, we're
she
converting
was.
to the same meaning, so we get the same result. Other things that have been historically difficult, we launched our Pat Inc. company in 2006 in San Francisco, and at that time if you said call Beth, no John, it would very happily give you the wrong answer every time. It would always call Beth. So call Beth, no Samantha, no John, no text. Right, so that's a series of error corrections, including changing the predicate from call to text. And if we said who was texted, John. Why is that important? Because in the current context, it's only stored text John. So statistically, that would be a hard one to solve. And we talked a bit about junctures today. So if we come here to junctures, just the introduction. When I first studied cognitive science, everybody was very enthusiastic about being eager to please or easy to please. So it's worth just covering that. So if Beth is eager to eat the sandwich, there's our juncture line. So what have we got? Beth is eager. So what does that mean? It means there's our predicate eager. Beth is eager for something. The X is undefined until we get the rest of the sentence, which is to eat the sandwich. And we've got to carry forward one of the arguments in order for this to work. But the end result is that Beth's eager to do something, eat the sandwich, and it's an active accomplishment, so the sandwich is consumed. And if we take the other example I said, Beth is easy for John to see. Because the predicate is the juncture meaning, we can then have lots of words with different meanings, but as long as it's going to a predicate, we can then resolve it in the particular sentence that's presented. And that seems to, we don't seem to have words in English, in my experience, where it means two different things, but you can use it the same way in a sentence ambiguously. So here's easy to please. So John sees Beth is easy. And time, Beth?
I'm
wrapping?
juggling.
Oh.
You've got 5 more minutes, 6 more minutes.
All right. So the best part's yet to come. So if we look at meaning, for example, here's the type of things that we can do with this system. Interleukin 33 acts synergistically with interleukin 12 and interleukin 23 on NK and NKT cells to increase the production of interferon gamma, further contributing to inflammation. And we've got the synergy being here, and we've got increase becoming greater, and we've got more inflammation. So it's possible to do things like PubMed examples. Not our first use case. And in conversation, if I just show you this is the one where when you exchange goods, the meaning really helps.
The man bought a car from the dealer for $1.
So if you buy something...
Who sold the car? The dealer did. Who
buy,
received the
sold,
car?
received,
The man did.
pay
Who
for...
Did the man pay for the car? The dealer.
Who is it sold by? So all of these things are simply taking the meaning of the question, comparing it to the meaning that we've stored, and giving us the answer.
What was the man presented with? The car.
And in terms of current context, we played around with different designs. In this case, it was easiest to have some of these other transitions so that, if you have possession, great, show it explicitly, but it's also in the main down here. Okay, back to you, Bess. So there's semiotic things. There's meaning everywhere. I like the C.S. Peirce contrast. So a sign is the words in a language or other things. Everybody's very focused on symbols, so word vectors are symbols. We just take all of this stuff and we map it to some symbol, and that's what you get. And then you have to try and find out indexes, which are the proforms, or icons, which seem to be impossible for large language models to deal with. For example, if you say, I'm facing north, my friend is on my left facing south. If I turn to the right, what direction do they have to turn in order to be facing away from me? And large language models have trouble with it because that's the definition of an icon. It's resembling the real world and the geography. It's not something that the word's telling you directly. It's also done in context. So bunch of different levels of work to be done. The verbs that we seem to have had a lot of in this morning's presentations because of the language. But also we need to distinguish between literals like the Wizard of Oz or my particular name and its meaning. Because depending on who you talk to, you have to use a different explanation. So if somebody says the Wizard of Oz is something, well, the first question that you'd probably ask is, do you mean the book or the movie? Or do you mean somebody who's the Wizard of Oz? What are you talking about? You agree what the referent is, and then you can keep going. And you can't just assume that the Wizard of Oz the wizard is a word, literally, when it could be part of a title. And again, in this case, if we've got the old man saw the Italian red car, after we've resolved the RPs, the layered structure is going to take saw and compare it to the PSA or the actor, and car is the undergoer, and make sure that everything's aligned with each other, which I think is just what RRG tells us to do. Here's how it looks in a patent. I did this a few years ago. After 10 years, the patents usually get approved, but in this case, I think it was 11 years. What we're doing is the cat ate the rat continuously. This is, again, from one of the RRG books. We're recognizing the components. Some of these are predicates, like when and where, but we recognize the components. That creates a set of things that we can now work with, and we then map it across following the linking algorithm to produce something that is going to be helpful for us. And so the thing on the right is just my layered model of semantics based on how I see it always working in RRG. You've seen this again, one more time. I give people examples of what these things are about. You know, logical structure is a good semantic representation. And I like saying that context is about something that we don't normally think about, particularly as computer scientists. We never think of this. So if Taylor married Ridge and you say, no, Brooke did, it's completely unambiguous that Brooke married Ridge. And if you have that example, that's also unambiguous. It was Brooke who married Ridge. But equally, if you just say no, what does no mean in this case? It means it's not true that Taylor married Ridge. And there's so much information in these very short words that we use all the time. And as a computer scientist, you'd have to write a lot of code to try and work out one sentence yes versus another sentence yes. I think this is probably the last technical one that comes straight out of the RRG verb classes. So if you've got the word see, the meaning see, in the center, I did an analysis of how often is that used in English. And there's activity forms like watch. It still means see, so I need to know if you're watching something, you're seeing it. There's an achievement, spot. There's causative, show, the state, see, and semifactive, glimpse. And that, to me, was good support that RRG is modeling something that the language actually uses as well as a shortcut. Like, rather than just say see intermittently, you could say glimpse, and you've saved yourself a lot of effort. So we'll just go through this in like 3 seconds. So the goal of the language-based system is, for any language that we choose, we just want to document how all the predicates work, and for each element in that predicate class, what are its selectional restrictions, and basically build a system, because I've been able to show that we can do some useful things with it at a good level. So there's lots of things to document, but keep going. This here, if you want to see what one of them looks like, I brought it along. This is one predicate class for feed, so causative eat. And I think there's like 1,200 things we're testing. Some of them probably were a bit over the top. So 1,080 tests, but I was looking at, tense aspect, negation, and all of those. I figure if you want to test, then maybe we're going a bit over the top there. But it was good to make me feel confident that this is doable. We need somebody to write these for each language, but there we go. So Beth.
Thanks, John. As John said, we've got a few projects on the go. One of them was the Speech Genie project. One was the early access that we're talking to universities about, so that you can look at the system that John and play with what John has showed you. If you want to read his book that he's just published, How to Solve AI with Our Brain, this takes you from his undergraduate years when he was sparked with the idea, or rather the challenge, of how to make machines understand human language and vision. We've got a few paperbacks here today. If you want to buy one and have it inscribed by John today, let me know, and we take cash or PayPal. Otherwise, you can order it online on Amazon. So we'd love it if you followed our work and maybe saw an opportunity that you could participate as we bring role and reference grammar with John's brain science to the world, with the first product being the language learning application. We've partnered with Chris Lonsdale, who John mentioned is a psycholinguist, language educator in China, and now we're going to be combining his very successful iOS application for teaching Mandarin speakers English. We're going to be supercharging that with the language AI that you heard about today from John. So today we're announcing we've got 2 new websites as of today, speechgenie.co and .jp. We're starting with 2 languages, English and Mandarin. So we'd love to have you visit our sites. You can follow us and be kept up to date. Because we're bringing the most awesome language learning system to you since language evolved. The brain being the first crack at it. The second project, as we mentioned, is the early access for education licence, and we'd love it if you were interested from wherever you come from, whatever university. We do book tours, and we love to present there at different universities around the world. With the vocabulary that exists in the tool today, you'll be able to see what John showed you, the language being broken down into meaning, and what that then means for conversation between humans and machines, and where we can go with that in the future. So we have some brochures, we've got cards, we've got things for you to take away if you'd like to visit up here at the end of, now, before we go to dinner. We have got question and answer time now for 10 minutes, is that right?
Yeah. So,
John?
thank you, John. Thank you, Greg. Yes. Lydia.
I've got a quick comment and a question. I'm very sympathetic of the idea of many of the things that you said, like that children don't learn language like a large language model does, or that language is not only purely associative, which is a big problem with large language models and so on. My quick comment was on when you talked about children, babies stopping learning sounds, and children not learning the statistics of language. There I would be a bit critical of what you said. Generally, as I say, I really liked the argument, but there is very serious experimental work that seems to show that children actually do stop hearing sounds, linguistic sounds, or understanding sound as phonemes when they've not been exposed to languages that have those phonemes. So there is some truth to this. And I would also think that statistics in the sense of frequencies play a big role in language acquisition. The problem is not that that argument is wrong. I think the problem is that you can't reduce language to associations, associative patterns. You can't reduce it to syntax because language is modular, and so you can't put, from my perspective, from the RRG perspective, you can't put everything into a single projection, or you can, but probably things work better when you match meaning with syntax, with context, which is what you are doing with your model. So I don't know if that makes sense, but I wanted to comment that. And my question is about, you said that you were working with, when you talk about it, you work with tense and aspect. How about even more abstract notions such as evidentiality, or evidentiality being, you probably know, I mean, manifesting
Yeah, it's obvious what you mean. That's an evidential, I think, obvious, but or it's apparent what you're saying. So firstly, the reason I chose Kuhl's work is that I think she's one of the top people in the field with the TED Talk. She gave that example, and I wasn't saying I support it or disagree with it. I was just saying I think we might find that we can move the needle in terms of improvement by doing different things that are not traditionally done. You know, like listening just the sound of a language for 20 minutes and then seeing if you've started to perceive the sounds in the language, and then repeating it until people get better at it, because it's been the experience of Chris Lonsdale and his company that it can improve. But I also accept, scientifically it says, no, this is how it works, and I think we might be able to prove them wrong to some degree. The second part of the question was evidentials and things. So we've done a lot. In the tool itself, there's thousands of examples that we put together, and it was the work of 7 or 8 people for 3 or 4 years, and I've been running continuously since I heard about RRG in 2012, with trying to get more, and Van Velen has helped significantly. Every time I've hit a roadblock, he then teaches me something that I was supposed to have known when I did the cognitive science course, like Grice's maxims and whatever, but he keeps steering me towards those types of things so that I can keep me and the team improving.
Yes, and I mean, I think you're right. It's probably, even when a critical threshold is gone for one linguistic ability, there are other linguistic abilities which allow children to learn, or people to learn languages also as adults. But
Right, and I'd love to see this this RRG conference where people are not only describing what's taking place, but also be able to show that this is what a system does when it's been set up with the thesis that's been proposed. But I'm ready to change the world, so I have lots of ideas like that, what we could do.
We still have time to more comments. Question here? Yeah.
This is just a very basic question. I think at the beginning you said that you were talking about ambiguity, and you said something that you didn't think people produced things that were ambiguous. And I was very surprised, because I thought the general view of that was people produce things that are ambiguous all the time, but that we're just incredibly good at using all of the contexts to ignore all of the other places. But I didn't think that speakers made any effort to avoid ambiguity. I thought it was that as hearers we're extremely good at eliminating. But I don't know if that's important or whether I misunderstood anyway.
Well, you know, when I come to the RRG conference and I say things, I'm always terrified of what types of questions I can be asked and what observations get made, because I'm a enthusiastic amateur on a lot of these things. On this topic, though, my understanding is that in context there's virtually no ambiguity, and that means we need to understand context a lot more than just recognizing the sentence and the possible interpretations. And we're at the stage with the system where we'll often get 2 or 3 meanings for a sentence. And then in context, you're able to work out, is this correct or not? So I use the example of the fish is off, the light is off, the party is off. And then I say what's off, and it'll say the fish, the light, the party. Then I'll say what is spoiled, it'll say the fish. You can sort of loop around it, but in order to answer those questions correctly, you have to test what the word off means. So if you, or what it, bad, you have to test what bad means in relation to the current context. And it took a few days to come up with that fix in order to get the system to pass those tests. So I think there's this incredible wealth of information that is waiting to be implemented on systems, which we're not implementing at the moment just because we've got this fascination with more and more statistics and more GPUs that are driving investment at the moment. But as I've listened to the talks today, I've just been impressed with the amazing amount of knowledge on a whole range of different languages, including sign language, that people could be exploiting in AI. I think I answered your question at the beginning of that.
One more? I think you can. There's one more.
Short question. You mentioned the fellow in Hong Kong who's you're working with. Thank you. And so I was wondering, how did they handle tone, pitch levels? Because in Mandarin, pitch is very important, and but it's mostly important at the word level, in the lexicon, as opposed to Africa, for instance, where it's really at the grammatical level. That's really, really crucial.
Yeah.
So, any comments on that?
I can just give you the background to it because I actually hardly speak English. This is the best I can do. I was American at one stage and now I'm Australian-ish. So Chris Lonsdale is a New Zealander who went to China when he was 17 or 18, and he finished up sitting on a train for 12 hours, and while he was on the train he was talking to the guard because he didn't have money for a seat. And during that time, between pointing and making sounds, he went from having no skill at other languages to having a theory of how he could apply language learning. And he then went on to speak Mandarin and Cantonese fluently. He was coaching CEOs, and then he went from that into this business of using this type of brain science. I really like the guy because we can just talk about brain stuff, and he's got so much experience from NLP, being the neuro-linguistic programming stuff, not the natural language processing. And so the things like brain soaking come from his NLP experience of what are the kids doing. Maybe we can replicate that. But in terms of the tone and things, I'd have to ask Chris or somebody else.
For you so that you can get in contact with us and ask Chris.
Okay, thanks.
Okay, I think we're in time, so thank you very much.